Welcome to qnawire.
Okay, so I've drawn out the problem here. Basic starting point. We start out with the velocity of 4.5 meters per second. And we're going to say that where it enters the zone with friction in it, it has we're going to call that position 0. And then at that point, the coefficient of friction is 0.1. So we know that the coefficient of friction is steadily increasing. So it's just kind of getting like rougher and rougher of a surface through here. And we want to know first of all, for part A, we want to calculate the stopping position. So the first step is to calculate the coefficient of friction as a function of as a function of position, x. So let's do that now. We basically assume, we know it increases linearly, we're told so in the problem. So we use that bit of information to do this. So we say mu at position x is equal to mu naught plus, this is just the slope-intercept theorem from basic algebra, mu1 minus mu naught over x1, x1 minus x0, right? And then once you plug those numbers in, you should get that this is equal to 0.1 plus 1/25 x. Okay, so this is an equation for how the coefficient of friction increases with x. Okay, so now we have to find the force of friction. New whiteboard, I guess. New whiteboard. Okay. Now we have to find the force of friction. And we know that the force of friction is equal to mu times the normal force, right? And there's an equal sign in there, right? But f and mu are both functions of x, so we have to be more careful about this. So let's write this more generally now. So force of friction at every point x is equal to the coefficient of friction at that point x, and let's make that a better mu at x times the force of the normal, which in this case is just force of gravity, mg, right? Right. Okay, great. So now we know we have the force of friction. Now, the reason we had to calculate this force of friction is because this is the retarding force. This is the force that's acting against the direction of motion that's actually going to work to slow it down. So basically, we know that all the kinetic energy that this thing had going into that rough patch is going to be the same amount of energy that has to be taken away from it before it stops. So we would normally just say, okay, the kinetic energy is equal to the work done on it to stop it, force times distance. Now that force times distance gets a lot more complicated. Now we have to say, okay, kinetic energy, the kinetic energy that this thing has when it's just sliding along freely, this is equal to this integral here. We're going to integrate over all positions from 0, x naught, to this place called xt, which is going to abbreviate for x terminal, so the stopping point. And we're going to integrate the force of friction over all x, all positions, right? Now, what's interesting about this is that this is effectively the force times the distance, but it's all these little tiny microscopic forces multiplied by all these little tiny microscopic distances. So basically, that's how you set up the integral, and then you just need to substitute in this equation that we have for force here. into the friction force where it goes. So let's do that. We just have to substitute in specifically our equation for mu. So this is equal to m times g integrated from 0 to x terminal times 0.1 plus 1 1/25. Oh, my stylus is not working too great. 1/25 x dx. And then to do that integral for you, let's get a new sheet up here. It's relatively basic calculus. It's pretty straightforward, but it's basically equal to mg names. Come on. Oh, this is weird. Mg times 0.1 x terminal plus 1/50 times x terminal squared. Right. And then if you remember, we set that up equal to our kinetic energy. So we can actually substitute in our equation for kinetic energy now. So we can just say that's equal to 1/2 m v naught squared. Right. Okay, so now I'm going to do a little trickery here. It's not actually that hard. You gotta be really careful though, because like I wrote this equation, this equals sign, equating the other, this half of the equation to the equation on the previous whiteboard. And now I'm going to kind of pull some sleight of hand. I'm going to say it's not equal to that anymore, and that'll allow me to cancel out this m with this m. So it doesn't actually matter how much it weighs now. Which is kind of interesting because you'd think that like a more massive package would slide farther. Just your intuition kind of says so, and that's not really the case. So anyway, yeah, so you can solve that equation, and then that'll give you an x terminal, and you can just solve that with the quadratic formula for x terminal. So I'll let you do that. And then if you want to find the coefficient of friction at the stopping point, you basically just put that x terminal back into your equation for mu. So you have then mu at x terminal is equal to 0.1 plus 1/25 x terminal. Yeah, and then C, how far would the box have slid if the friction coefficient didn't increase, but instead had the same constant value of 0.1? Well, in that case, let's just put a little divider here. Oh, come on, stylus, you got it. Okay, so if mu is just 0.1, well then the force of friction is constant, it's just mu mg, right? Then we can just go back to our normal equation, 1/2 mv naught squared is equal to mu mg xt. Right, just our normal equation. We cancel out the m's, and we solve for xt.